Hey everyone, this is Brian. Welcome to week 8 of CSC 143. Hope you had a great weekend. Long Memorial Day holiday weekend, that is. Your project 3 is due today if you're watching this on Wednesday, and it's already been due if you're watching this on the day after Wednesday. And your project 4 comes out now. Project 4 is going to go over sorting algorithms, heaps, and hash maps. We, of course, have been learning these things over the last couple of weeks, and I think it's about time for us to write them in code and actually implement these structures by hand. And it's going to seem intimidating at first, especially this hash map structure. But what I think it really gives you is an appreciation for what really happens in these underlying library structures and how they organize this data to associate key and value pairs. And while we're on that topic, I do want to quickly talk about the reading that I had to do last week about mutable keys. Now, if you don't know about mutability, something that is mutable essentially means that the object can be changed in terms of its underlying values. So take a pair object, for example. It's just an object that stores a left and a right field. We see that pair is mutable if the left and right fields can change after they've been initialized. So this is doing something like pair.left equals something else, or pair.right equals something else after it's been constructed. A class or object is immutable if its fields cannot change after construction. That is, the moment it's constructed, that block of memory for that object stays exactly the same through the lifetime of the object. Now, one consequence of this, immutability versus mutability, is that when you use key types inside a hash map to associate with a value, it's not going to necessarily enforce that those keys are immutable types. So let's say we're using a hash map, we're associating a pair type to a string type, and the pair itself is a mutable type. Let's say we can change the left and right fields. If you remember, the hash code is something that's derived from the underlying values of the object itself. So maybe a sensible thing is to take the hash of the left field and the hash of the right field inside the pair to generate the hash code of the pair itself. And as you also recall, the hash code is very important for determining which bucket the key itself is going to be placed into inside that hash map. So that way, when we can invoke the hash code function on the object, we determine which bucket it's in, and then we can find the value associated with that key. Now imagine we are using a series of pairs, we're associating with strings, everything's fine, and then we actually modify one of those pairs by updating their left field or their right field. The consequence of this is now the hash code function is going to produce a different result than it was originally. So if we had an association between that pair and a value that was based on its original hash code, and then we modified that pair such that it now produced a new hash code, we can no longer actually get back to that original association that we made between that pair and that string that we had originally intended based on the original hash code. This is pretty dangerous. It means that if you're using keys that are potentially immutable, it's also possible to actually completely lose the association between that key and its respective value if that key has changed in such a way that the hash code of the key itself has also changed. This is actually perhaps the cause of a memory leak. If we can never get back to that old state where that pair gives the old hash code, then there's actually no way to retrieve the original value association between that old pair and this new value. So I think the moral of the story is when you're using hash maps and you're deciding on the type for your key and the type for your value, it's important that for the type of your key, it should be an immutable type. It's a type that's not going to change over time, and you should use fixed values like strings or integers or pair with final fields so they can't be modified, such that you're not going to run into this problem of having keys that end up being mutable in the future and cannot actually be used to look up values it was once associated with. Okay, that's enough for me talking for today. This week we're going to take things pretty easy. We're going to learn about functional programming in Java, which is kind of a fun side topic. I think there's like maybe one small quiz or exam question about it, but I wouldn't stress about it too much. It's more of a fun little diversion to let you explore how maybe other languages handle the concept of programming and how Java has inherited some of these features in its own language specification. Cool. Thanks for listening, and please enjoy the video. Hey everyone, this is Brian. Welcome back to another video lecture for CSC 143. In today's video, we're going to be going over functional programming in the Java language. And functional programming is one of these concepts that I'd like you to be familiar with before you leave this class. Let's get started. And we'll kick things off with a discussion on static methods. We've said how methods in Java are functions attached to instances of a type. So here I've got a class square type that perhaps implements the shape interface. The square has a width variable, and inside the shape it implements this area method that returns a type double that, as you'd expect, is going to return the area of the underlying shape. By nature of the area method, referring to one of the instance variables of the square itself, the area method has a dependency on the instance and its underlying state. So when I have an instance of square and I invoke its area method, it's going to return the specific area for this specific square instance as the return value of this method call. So in this square class, the method signature of this area method is going to not only define the method, but also how it gets called. We see how area the method returns a double and takes no arguments. There's nothing in between these two parentheses here. That being said, there is an implicit argument. The instance this. The area method cannot live without a square instance to attach to, a this reference to refer to, and a with property to look up. Sometimes we want to write a standalone function that doesn't have a hard dependency on this kind of instance. Here I've got a shapeUtils class that, as you can imagine, is like a utility class for all sorts of helper methods regarding shapes, and the public static void print area method takes a shape as an argument and simply invokes the area method and prints it into the console to get the area of the shape on the way out. And what's special about this static method here is that because it doesn't have that implicit this argument by nature of it being static, the print area method cannot refer to and is not obligated to and will not refer to any sort of instance, any sort of live instance of shapeUtils. Instead, we can just go about invoking shapeUtils.printArea with no instance at all. We can just look up the method reference directly and invoke it directly, no instance necessary. Here I declare a new shape, I assign its width variable to 5, and I can call printArea just on the basis of the class itself without needing to construct an instance of shapeUtils first. So the closest thing to a standalone function in Java is a static method. The static method is attached to the class definition, not an instance of it. One well-known use of a sort of standalone function is a comparator. And we've seen this comparator within the comparable interface. Remember that the comparable interface describes classes which have a natural ordering. That is, these instances can be sorted, such as within a binary search tree, and therefore they must be comparable to each other. A class which implements the comparable interface is obligated to supply a compare_to method based on how the current instance, this, should be naturally ordered to the argument object that's being passed in. The interface is a generic interface with a generic type t that indicates that whatever class is implementing this interface can be compared to other types of type t. The general contract for compare_to in Java tells us that if the current instance comes before the argument in terms of ordering, we return -1. If the current instance and the object being passed in are equal in terms of ordering, we return 0. And if the current instance comes after the object being passed in, we return a +1. I have a remark here. In a different universe, we might have used something like an enum, like before, equal, and after, instead of -1, 0, and 1. So why did we settle on using integers as a return type for the compare_to method? Well, as it turns out, there's a pretty convenient shortcut that we can do by nature of us returning an integer type, which is actually just to return something negative, 0, or positive to return before, equal, and after in terms of ordering. And the fastest way to do that is just to do some math, like this.x minus object.x when I'm comparing a number with another number. Let's go visit circle.java and circletest.java to see how it all works. Okay, Here's my circle class. It implements the comparable of type circle interface, which means that circles should be comparable to other circles. Within my circle, I have two fields, the integer radius and the string name, which I'll initialize inside my constructors. Now in my compare2 method, what I'll go ahead and do is I'll specify the natural order of circle by its radius. Remember that this is a custom class. I am personally defining what the circle is, so it is up to me to decide how to naturally order these circles. And I'll go ahead and say that their radius takes priority. So let's say that we want to organize these circles by their radius in ascending order. We can compare the radii of the current and argument circles. If they're the same, return 0. If the current radius is less than the argument's radius, return -1, otherwise return 1. The one-liner equivalent of all of that is actually just integer.compare, which is a static method that lives on integer that fulfills this contract of compare2, and it's going to give me a positive, 0, or negative number based on how the two arguments get ordered. Okay, so I've gone about and defined this compare2 method, and I've decided personally as the writer of the class that it's going to be based on radiuses. Let's go visit the circle test to see how it comes into play. All right, I've got two circles, one with a radius of 5 and one with a radius of 10. I should expect that the radius of 5 circle comes before the radius of 10 circle, and the radius of 10 circle comes after the radius of 5 circle. Makes sense? And then if I build a new circle with a radius of 10, then the existing circle that has a radius of 10 is going to be ordered the exact same way as this new circle that I've just declared. Now that I have fulfilled that compare2 method, I can actually use it in Java's provided native sort algorithm. Here is a list of circles. I've constructed it using this helper method arrays.asList, which is going to translate all these arguments into a list-like structure. So I've got a circle of radius 1, 9, 3, 0, 3, and 7, and I packed it onto a list containing the circle type. Then I can invoke the sort method, which is provided in the collections utility class in Java, that accepts a single list argument and is going to, in place, modify that list such that the elements inside become sorted in order. Here's my expected list. I'm expecting the circles to come out in 0, 1, 3, 3, 7, and 9 order, and I see that that is indeed the case. My assertion is going to pass that my expected list matches my circle list that started out in unsorted order. We'll give it a minute to compile and run. There we go. So the nice thing about having this standard interface for classes to follow that declares the class as being comparable to other instances, we can start to write other Java, or we can start to use other Java standard library functions that depend on this standardized interface. The collections method in Java, or the collections sort method in Java, is going to invoke this compare2 method that I have supplied on the class instances, which it knows must exist because the arguments that I'm passing in to collections.sort are of a comparable type. So here's just that shortened example. I've got a list of numbers 1, 5, 2, 3, and 10, and I can sort it by nature of those numbers being comparable, and the sort method is going to, in place, rearrange the elements within the list to be 1, 2, 3, 5, and 10. Now, unlike the equals method, which we have seen inherited by every object, because the equals method is defined in the top-level object class, the comparable interface is optional. Comparable classes need not be comparable. We can build classes that don't have a compare2 method, and this has always been the case. Why is that? Why is there a distinction between the equals method and the compare2 method? Shouldn't every class have something like that? Well, the Java engineers decided that we should always have a way to determine if two class instances are equal to each other by value. But we do not necessarily have to have a means to compare two instances by value. And the comparison analogy doesn't really extend to everything in the universe. We cannot naturally necessarily compare something like water bottles. We could certainly define them as big to small, but what about these other dimensions that you might think about, like color or features or stickers or something like that? We, as the developers who work with a Java programming language, now have the option of deciding whether or not my class is going to have any set of dimensions that it can be used to compare against other instances of the class. And that may not necessarily be useful, not nearly as much as useful as this equals method, which is going to determine if two things are exactly the same, which I would say is a much more common requirement to know whether two things are equal to each other, not necessarily how they belong in a certain ordering against other instances. I want to talk a little bit more about this comparator, that method that we had written to compare two instances between each other. A comparator is a function which compares two objects to define their order. The compare2 method is that comparator that we just written, supplied by a class definition itself. However, we may not always want to use the native comparator method supplied by the class instance. We may want to arrange instances based on a different kind of comparison. So maybe we've got a people class that naturally sorts by name, but instead we like to sort it by age. We've got a vehicle class that naturally sorts by price, but we want to sort it by weight instead. We have music that we'd like to sort by release date instead of popularity, or maybe in 2 dimensions, we want to sort by release date and then popularity to break ties. A very common example, what if we want to sort in descending order rather than the ascending order that is by default provided by all Java number types and all comparable types? We could do a number of things to make this happen. The first thing we could try is to modify the compare2 method itself inside the class. And this is pretty obviously, I think, not a good idea. Classes are open for extension, but closed for modification. That's what the open-close principle tells us. We cannot just go into these base class definitions, these fundamental classes that are used in several places, and monkey patch their underlying compare2 methods to do what we want them to do. That is going to violate expected behavior in a lot of places. Imagine if I went into the string definition inside Java and changed the compare2 method to, rather than sort by ascending order, sort in descending order instead. Suddenly, everywhere in Java that a string is used, whenever compare2 is invoked, it's not going to behave as expected, except in the places where I'm invoking the compare2 method. So this is obviously not a good idea. What else can we do? We could try extending the class and then overriding the compare2 method, which is also not good. What was one of those principles we learned? The Liskov substitution principle. That told us that we should be able to substitute a child class anywhere a parent class belongs without any external clients being aware of the substitution. If I override the compare2 method to do the inverse of what the original compare2 method did, then in another world where different references to the parent class are being used, if I pass that class an instance of my child class with this modified compare2, suddenly I now have a method that is going to behave completely differently than the same method on the same kinds of references in other objects that are the parent instance. So that's not good. The thing that we could do is we could write our own sorting function. We could write a sorting function that examines the underlying state of the variables. We could return whatever order we'd like. But that's not so good because that's a lot of work. We've seen how troublesome it can be to write something like a merge sort or a quick sort. Ideally, we just have this one standard approach for sorting that's provided by the library itself, and we don't think about it ever again. Ideally, we would have a way to reuse the existing provided collections.sort method and supply our own comparator without having to do one of these kind of crazy things above. On top of the comparable interface that we just learned about, the comparator interface in Java, note the slight difference in spelling, comparable versus comparator. This is a comparator. The comparator describes a standalone class with a method compare that takes 2 arguments, a left and a right, that can be used in place of a native compare2 method that's supplied by an instance of a class. Let's go visit the official Oracle Java docs to see what that's like. Okay, we've got our interface comparator. The single generic type is the type of objects that may be compared by this comparator. And we see how the comparator describes a comparison function that imposes a total ordering on some collection of objects. You can do a little bit more reading on your own if you'd like to know more details. If we scroll down, we see how the compare method is a requirement of the comparator that has to be fulfilled by the class itself. It's an abstract method. It takes two arguments, O1 and O2, and it's going to compare its two arguments for order. It should return a negative integer, 0, or a positive integer if the first argument is less than, equal to, or greater than the second argument. Let's go see how we can build our own comparators to use with this circle class that we've just talked about. In circle descending comparator, I'm going to provide a comparator method that's going to sort the circle in descending order rather than ascending order that we saw in the previous example. This class implements the comparator of circle interface, which obligates me to implement a compare method that takes two arguments, a O1 and an O2 of the type that I'm comparing against, the circle, and return an integer. And to fulfill this method, what I'll do is I'll return -1 times the native compare2 method provided by the circle, which compared circles in ascending order according to the radii. So in effect, this comparator is the same as the circle's native comparator, but just inverted, so the ordering is going to be backwards. Now let's go see how that gets used. Here's my circle descending comparator test. I define a list of circles, 193037, and when I invoke collections.sort, not only am I going to include the circle list as the first argument, but I will include a second argument, which is an instance of the circle descending comparator. And this circle descending comparator is a class with one method defined, that compare method, that is going to invoke circle's native compare2 method and just reverse whatever decision it makes. It'll multiply that result by -1. The outcome that we get is my circle now comes back, my circles now come back in inverted order. I get the circle with the greatest radius of 9 first, then 7, 3, 3, 3, or 1, and 0. This is of course backwards from what we had got with the native comparator of 0, 1, 3, 3, 7, and 9. Okay, so that's pretty useful. I can pass in my own comparator as an argument to collections.sort and have collections.sort use that in place of the circle's native comparator. Let's go a little bit more advanced and check out circle name comparator. Remember that second property, the string name within the circle? I didn't actually use that inside my original compare2 method. But what if I'd like to? What if I'd like to sort my circles by name rather than their radii? In my circle name comparator, I can define just that. Once again, I have a class definition that implements the comparator interface of type circle, which obligates the class to provide a compare method that takes two arguments, O1 and O2, and I will say that I would like to compare my circles by their name, and I will do so using the native compare2 method supplied on the name property of type string. I'll set it up such that I'll get the natural comparison of the two circles' names, and then, you know what? If those two names are identical, I will just fall back to the default radius comparison provided by the circle itself. So the great thing about being able to define your own comparator inside this method definition is you can not only compare across different properties, but you can continue to use the existing native comparison as a fallback. So names are going to come first as priority, and then I'm going to break ties using their radii. Let's see how that works in the circle test. Here's my circle name comparator test. Whoops. Once again, I've got a list of circles. This time it's a bit longer. I've got my radii 1, 9, 3, 0, 3, 7, and 8. But this time I've also given every circle a name. Frank, Bob, Eli, Charlie, Daniel, Alice, and Alice. My circle name comparator is going to prioritize sorting by name first and then break ties using the radius field. So when I pass an instance of the circle name comparator to collections.sort as the second argument, then the list I get on the way out is going to sort by name first. So it's going to place these two circles with Alice in the very front, and it's going to place the bigger circle after the smaller circle because that is the native ordering where the radius is used to compare the two circles, now that Alice and Alice have equal names. Then for the rest, I see they are sorted in expected order. I've got Bob, Charlie, Daniel, Eli, and Frank. And the radius fields are not considered in these cases because the string names take priority. So what you might find is an interesting design choice. Comparator does not make compare a static method. Instead, it is an instance method, and the type itself, the comparator, the instance, must be constructed. Let me go back to the test to point that out. Here when I called collections.sort, which itself is a static method, I pass in two arguments, the list to be sorted, as well as an instance of my comparator. I'm invoking the new keyword here. I have to actually build a brand new instance of this class that is otherwise empty beyond its one method declaration, which is compare and returns an integers. It may seem kind of strange that this is necessary. What's the point of building a brand new instance of this class if there's nothing in it beyond this one method call that doesn't even refer to the implicit this argument? Could not this method be just a static method? What's the point of us having to build an instance? And it definitely seems strange until you realize that Java doesn't actually let you pass something like the class itself. Let's suppose for a moment that I tried to pass a static method to collections.sort, and I did so by passing in my comparator class definition that had a static method inside compare. The problem here is that there is no real method signature here that collections.sort can accept that is just the type itself. We can't pass in just this type. We have to pass in an instance of the type to be used as a particular argument in this location. Here we are doing just that by passing in a fulfilled instance of the comparator interface by actually providing that instance as an argument, such that the methods can be invoked on the instance itself. Now, there are some special language features in Java that you could use to get around this weird limitation of not being able to provide a class and having to provide a class instance. There's a feature of Java called reflection that permits this. Reflection is a bit of a language hack that makes Java act like an interpreted language. It allows Java to look at these class definitions sort of retroactively, reflectively, and invoke methods upon them that are named in a particular way. This is out of scope for this class. It is sort of neat, but it's not really in the vein of, I guess, good compiled code because it involves looking through the class definition itself, but it's kind of neat to think about. So in summary, while the comparator interface solves this problem of having to substitute methods, that is, I can pass along a comparator as an argument, as a sort of package for a method, it is unwieldy to use. We have to define an entire external class that fulfills the comparator interface and construct an instance of the class just to use it. We'd like a better way. A way just to pass a function as an argument. Nothing more, nothing less. Let's zoom out a little bit and ask ourselves, what is functional programming? In this class, and in all the previous computer science and programming classes you've taken, you have learned what is called imperative programming. Objects have internal state, That is the object-oriented part of object-oriented programming. Modifications to this state happen via methods. This is something called procedural programming. And the methods are written as a list of statements. Imperative programming. These kind of statements are things like variable assignment, control flow statements, like loops, and method invocations, which of course are composed of more statements. The reason we call this imperative programming is because every statement can be thought of as an imperative to the processor to go do something. When I perform this assignment of int x equals 5 plus x, I'm sort of saying, processor, go figure out what 5 plus x is and place it where x belongs. With these control flow statements, like the for loop, I tell the processor, I would like you to repeat this step repeatedly until a certain condition is met. There are some drawbacks to this programming model. The first is that methods and function calls hide behavior. The side effects of a function call are ambiguous. When I say side effects, I mean any effects of the function beyond whatever internal computations that have to happen for the function itself to run. For example, let's suppose I had a list and I invoked the clear method, which is probably going to delete all the elements of the list. Does that method actually do what we expect it to do? What if it has side effects like printing to the console? What if it writes to the file? What if it reads from the network? The method call itself is ambiguous in the intent of the method. Sure, we could go read the documentation, we could go look into the method call itself, but the more high level we get when we write our program and the more we depend on these sort of abstractions, the less familiar we are with the internal implementations and the possible side effects that they can have just from looking at the method signature. The parameters passed to these methods hide the underlying object. MyList.clear doesn't actually take any explicit arguments, and the this argument is implicit, as we've talked about. Parameters that we pass in to the method as arguments may actually get modified. If I have a method called join that takes in a list, and this method is available on existing list, does the list that we pass in get destroyed? When I join the first list to the second list, does it steal the elements of the second list, or does it copy the elements of the second list? The method signature itself is too ambiguous for us to know. And again, we don't know how this method is necessarily implemented. It may do things that we don't necessarily expect, like the destruction of the argument that we pass in. So while this encapsulation, these method calls attached, these method definitions attached to object instances, is a useful tool for abstraction, the methods themselves are arguably harder to test for correctness, because object state can be infinitely complex. Here's a very simple class definition. Class A has an integer I, a double B, and array list of integers C. There are infinite possible different instances or states of class A. I could define basically infinite, virtually infinite, A objects, object instances, and have their internal fields be all uniquely different. This is especially the case with this array list C here. Array lists have theoretically infinite length, so long as I have sufficient memory. I could have instances of A which all have different varying lengths of C with all different numbers inside. The challenge then of testing the correctness and validating the correctness of this class definition as well as its methods is that the internal state of the class can be infinitely complex. There can be an infinite amount of combinations for these different variable assignments. And for that reason, we may find it incredibly difficult to find certain edge cases or complex scenarios where these methods behave unexpectedly and erratically, depending on this internal state. We could do some basic testing around the numbers of I, the numbers stored in B, the kind of numbers stored in C, but we cannot get complete test coverage in terms of the universe of possible items that can be stored within these variables within the class. Functional programming is going to take a different approach. Functional programming is based around the idea that rather than we write procedures, line-by-line instructions that tell the computer how to do something, like those assignments or those for loops, we are going to write declarations that tell the computer what to do. And if we can guarantee that every declaration is correct in their implementation, a series of declarations will always be a correct program. We are going to tackle this idea of writing correct declarations by observing how pure functions fulfill that role. Consider the following absolute value function. Public static int abs takes a single argument x. If x is less than 0, return the inverse of x, otherwise return x. So every time I pass in a number into abs, I'm either going to get the number multiplied by -1 if it's negative, so I get a positive number on the way out, or I just get the number itself, which is already positive. Let's make some observations about this abs function. The function itself is pure. It has no side effects. We can see how the argument does not get modified. X is not replaced. X does not dereferenced in any way. X is a primitive type, so it's actually a copy, so it can't be modified. At least the calling argument cannot be modified. There are no variables outside of the function that get modified. There's no global variables that are accessed here. There's no library code that gets touched. No system calls are invoked, like print line that writes to the console, or there are no attempts to write to a file or read from the network. All the information needed for the function to run is in the explicit argument int x. There's not even an implicit this here. The function itself, being a static function, is not attached to any instance. The function has no influence over any state. We also see how all calls to the function with the same argument always produce the same output. This function is predictable. It is deterministic. Every time I call abs with a specific number, I can do it an infinite number of times, and it will always produce the same result every time. The compare method from the comparator interface, remember comparator obligated us to write a compare method that took 2 arguments, can be pure. If we write a comparator that only uses the arguments and causes no side effects. However, compare is still an instance method. Remember how we talked about how compare is not a static method. Compare is still an instance method of an instance of a comparator. So there still is an implicit this argument. So this compare method here still suffers from the same problems of object-oriented programming methods, as we've described. So let's zoom out a little bit more and talk about higher order functions. A higher order function is a function that takes a function as an argument. The collections.sort method that we've observed takes 2 arguments, a list argument, which is the list to be sorted, and a comparator, which is, of course, an instance of that interface we've talked about. Collections.sort can be thought of as a higher order function because the function itself, that is the sort function, accepts a function as an argument, which is packaged inside this comparator. Then the compare method inside the comparator, inside the argument that gets passed in, is invoked upon the pairs of elements in the list. Okay, that's nice, you say, but we still want to tease apart the method compare with its class. So again, let's keep our eyes on the prize. We'd like a way to pass only a pure function as an argument, not an instance of a class containing a function. And that brings us to lambdas. Formally, a lambda is an anonymous function. It is a function without a name. We've seen a lot of things already on the way leading up to lambdas. We've talked about functional programming. We have talked about pure functions. We have talked about higher order functions. And now we are discussing lambdas and how it belongs in this list of ideas. Lambdas are anonymous functions. They are functions that stand alone without a name. Unlike static methods or even instance methods, lambdas do not even attach to classes. Instead, they can be treated like a value expression, like 1 plus 1. In Java, the syntax for lambda is as follows. Arguments, arrow, return value. And this arrow, by the way, is literally a dash and a greater than sign. Remember, we're motivated to learn about lambdas because we like to fulfill the higher order functions requirements of a function being passed in, and we'd like to provide something that looks like a pure function so that we can write these perfect, correct declarations in functional programming. Okay, so here are how lambdas look. We have argument on the left, arrow, and a return value on the right. And that is really all that is. The following expressions below are all lambdas. If there is no return statement, the expression on the right is returned. A returns A times 2. A and B returns A plus B. 2-argument lambda, integer A and integer B, returns A plus B. These are all lambda expressions. The entire line represents a lambda, and itself is an expression just like how 1 plus 1 is an expression. If you'd like to use multiple lines, we can write a curly brace block and use an explicit return statement. Here is a longer lambda, it's a multiple line lambda, but it still is a single expression. This lambda takes 2 arguments, a circle A and a circle B, and to execute the lambda, we compare the name of the 2 circles. If the names are the same in terms of order, we are going to return the native comparison method, which is going to use the radius field on the circles. Otherwise, we'll return the string ordering. This entire expression is a lambda. It is a standalone function, and it is a standalone expression just like 1 plus 1. Wow, easy. Can we pass it on to collections.sort as the second argument? Let's find out. Here is the lambda test. And in lambda test, I'm going to start out with the same list of circles. I've got radii of 1, 9, 3, 0, 3, and 7. I've given them all names: Frank, Bob, Eli, Charlie, Daniel, and Alice. But rather than passing a comparator, an instance of a comparator that is, to the second argument of collections.sort, I'm going to pass in a lambda expression. I start out a lambda expression with a list of arguments, which I have 2 of, a circle A and a circle B. I have an arrow and a curly brace block. Then I fulfill this lambda expression's body with that comparison algorithm I talked about. I will depend on the name first and then fall back to the radius if necessary. I can pass in this lambda expression as a substitute for that comparator interface. And collections.sort is going to invoke this lambda in order to compare 2 circles against each other for the purposes of sorting the list of circles. And here down here, in the expected list, indeed we expect that the circles get sorted in name order. Let's run it just to be sure. Great. So can we pass lambdas as arguments to higher order functions? Yes, we can. We can have collections.sort take a lambda as a second argument rather than an instance of a comparator, and have it use that function in order to compare 2 circles for the purposes of sorting. We can use lambdas that are not attached to classes or an instance of a class to pass a function as an argument to another function. Sadly, as with many things in Java, lambdas have some baggage. Let's go take a look at the method signature of collections.sort again. And if you control-click into collections.sort, let's actually go do that right now, you can see the complete method declaration. Here we see that sort is a method that has a single generic type, t. It does not return anything as a void, and it takes 2 arguments, a list of type t, and a comparator that is capable of comparing type t itself or children of type t. Then it's going to go pass this list along it's going to go actually invoke the sort method upon list with that comparator as an argument. So what I want you to observe here is that even though I'm using a lambda as the second argument to sort, I'm still somehow fulfilling this argument requirement of the comparator interface that itself, remember, required me to have an abstract method implemented, the compare method that took two arguments, a left and a right argument for the purposes of comparison. So when we pass along that comparator lambda to collections.sort, we are in effect passing an object that fulfills the comparator interface. Remember that comparator, as we just talked about, requires us to fulfill a compare method that returns an integer. So this raises an interesting question. How is it that the lambda itself can fulfill this obligated requirement of needing an object instance of a comparator that fulfills this compare method when the lambda is just a standalone anonymous function? Clients of the comparator expect a compare method that is attached to an object. Well, as it turns out, in Java, lambdas may substitute interfaces that have a single abstract method. An interface with a single abstract method is called a functional interface. This is a Java-specific term. The name of the abstract method does not matter. So long as there is exactly one, a lambda can be used in its place. That lambda will replace the functionality of that single abstract method regardless of what that method is named. For the substitution to be valid, the lambda must have compatible arguments, a compatible return type, and check out the reading for some more details. Let's go check out a sample functional interface. Here is my sample functional interface. It's an interface that has a single abstract method declaration, which is sum can be named anything. Takes two arguments, integer A and integer B, returns an integer type. What I want to emphasize here is that so long as the interface itself has exactly one abstract method declaration, it doesn't matter what the one abstract method declaration is actually called. Because when I try to fulfill this interface using a lambda, that lambda will automatically fulfill the role of the only abstract method that's available in my interface. Let's go take a look at that lambda test file. Here my sample functional interface gets fulfilled by a lambda that's just taking two arguments and returns the sum of those two arguments. I call this one lambda sum. Remember, the sample functional interface has exactly one abstract method, and I just need to fulfill the arguments and the return type of the method for my lambda to be compatible. Let's check out the second one here. Sample string integer interface functional, ls. And we'll go ahead and also use the exact same lambda. I've got two arguments and I return the arguments added together. But how is it that these two lambdas are the same? When, if I go examine sample string interface functional, I see how this interface has a single abstract method that is called literally can be anything, takes two arguments, a string A and a string B, and returns a string, rather than two integer arguments and returning an integer. Well, it turns out in Java, you can add two integers together using the plus operator, and you can also concatenate two strings together using the plus operator. So despite the fact that there are no type signatures here in the arguments or an explicit return type, Java can figure out that the type you are returning and the types you are accepting as arguments are indeed compatible with the lambda itself. And it can go intuitively match the types of the arguments with the types that you're providing in the lambda, as well as the return type. Here in my assertion on line 49, I'm invoking lambda sum can be named anything, and passing in two arguments 5 and 10. Remember that lambda sum has a single method, and typically, if I were to fulfill an interface, I would do so using a concrete instance of a class that has fulfilled the method's abstract method, the class's abstract method requirements with concrete method implementations. So lambda sum is obligated to have a concrete method implementation where sum can be named anything, and the lambda expression is going to fulfill that method declaration. So I can actually invoke sum can be named anything upon the lambda sum interface, because Java is going to treat that lambda as if it were the fulfilled concrete definition of sum can be named anything. Only the method signature of the abstract method has to match. The actual purpose of the function doesn't have to matter to the compiler. Remember my sample functional interface? Sum can be named anything. I'm calling this one lambda divide. It takes 2 arguments and returns the first argument divided by the second. Despite the fact that some sample functional interface has a method called sum can be named anything, it doesn't actually matter how you fulfill that interface, because remember how interfaces don't specify how the underlying methods are actually fulfilled. They're not going to enforce that kind of correctness. Here, so long as the method signature matches and the return type is correct, I can pass in any lambda to fulfill that functional interface's abstract method. Here, once again, I can invoke sum can be named anything upon my interface, and this is going to go use that lambda as if it were the concrete method implementation for the abstract method declaration inside the interface. 10 divided by 2 gives me 5. The comparator lambda that we've seen in the previous test fulfills the method signature of the abstract method compare in the comparator interface. Let's check this out. The comparator of type circle obligates us to implement the compare method that takes 2 arguments, 2 circles, and returns an integer. I'm going to fulfill that lambda requirement by having a lambda that takes 2 arguments and returns an integer. So I've removed myself the obligation of having to go build a complete class and define a compare method just by using this lambda expression to take the place of that one abstract method that the comparator needs in order to operate. This is basically the same as if I had written down a comparator inside of a class like SQLNameComparator, which, as you remember, is a full class definition that fulfills the interface with a compare method defined. Except I've extracted that method implementation into a standalone lambda. I can use my lambda comparator to compare 2 circles, and I can invoke the compare method, which could technically be named anything, because my lambda is going to fulfill the only abstract method declaration inside the comparator. And here, finally, I can indeed invoke sort on my list of circles and pass in my string comparator, which is a standalone lambda. One last thing, check out this void lambda. In my sample void functional interface, I have a single method declaration that takes no arguments and returns nothing. Can we write such a void, no argument lambda? Indeed we can. If you'd like to do that, put down some parentheses with nothing inside to indicate no arguments, and then return an empty set of curly braces, which is essentially a function block that has no return no return statement. So there is no return from calling this lambda. So what actually happens, what enables these lambdas to fulfill where what we would usually expect is a concrete object instance, Java is actually going to construct a concrete instance of the interface where the lambda substitutes the abstract method requirement. If we go back to the lambda test, we can validate that it is indeed going to build these objects for us, just behind the scenes. String comparator is fulfilled by this lambda, and typically interfaces have to be fulfilled by concrete objects. So what's kind of funny is I can invoke things like toString upon the string comparator. ToString is a function I get from the top level object. I can also invoke things like hash code. And it's a little bit silly to see this because remember the comparator is supposed to be, the lambda fulfilling the comparator is supposed to be a standalone function. It's not supposed to have this kind of class overhead that we see with full class definitions. But Java is going to go do that behind the scenes for us. It's going to go build out these objects on its own. It's just going to be much cleaner for us to write. Java is not going to require lambdas to be pure functions. I think it's ideal that your lambdas are pure functions because that makes them good, compact, testable functions. But they can be, so you should strive to make them that way. A+ for effort. A+ to the Java language engineers. Is Java a functional language? Not really. Java is first and foremost an object-oriented programming language. Objects and methods are a core part of the Java language design. However, since Java 8, Java has introduced several functional programming features that let developers take advantage of both object-oriented programming and functional programming patterns. In your last project, where you've written a bunch of recursive algorithms, you may have seen this block of code inside the test suite. Here, my binary tree algorithms in order method is going to go return an in order search representation of this binary search tree that I'm passing in. And it's going to go print out, well, it's going to go return a list of values and save it in the in order variable. Then I'm declaring this variable output that is in order, which is a list of values. I invoke the stream method upon it, which is a method available on list. And stream is going to pass along the individual items within the list itself, kind of like a for each loop. And I'm going to invoke the map method upon the stream. Map is going to invoke a function upon every element that's passed to it. So it's kind of like invoking this function toString upon the elements inside of a for each loop of the list. Then the collect method, which is chained upon the result of map, is going to join the result of all the mapped elements using the space string. And the outcome is that I'm going to get a single string of characters, which is produced by the call to collect, where the values in the list are the string form of the values separated by spaces. The alternative to this would be writing that for each loop, invoking toString on all the objects, then appending them all to a string with a space in between. Here, my functional approach is going to do it step by step, and it's going to use these piecemeal functions like toString and collectors.joining in order to do the same thing. I get the benefits of functional programming because I get standalone functions that are well-defined and have predictable behavior. Map is always going to do the same thing regardless of what list of items you pass to it. It's always going to invoke the method passed to it, the function passed to it as an argument against all the elements on the list. The collect method is going to do something similar. It's going to go figure out how to join all the elements of the stream in a way that is defined by the function that gets passed to itself. So we have broken up what would usually be a step-by-step procedural function definition into a whole bunch of little function definitions that we can all test and validate independently. Okay, functional programming is something that you might see in other languages, and you will most assuredly see in your computer science career. It is something that's picked up a lot of steam over the last several years because of some of the benefits of having really nice, small, compact, testable functions that can be reused in a lot of places. I hope you enjoyed learning about this new kind of programming style, and I hope you can take advantage of it in your future programming life. Thank you for listening, and I'll talk to you next time.